Okay, so picking up from last time, standard announcement, same announcement before. Muddiest Point this Sunday, mini project 2. So that's evolution strategies, immunocomputing, and genetic programming. If you're interested in any subset of those, then feel free to think about coming up with a mini project, a 2 to 3 page demonstration of one of those concepts, not all of them. And that is due here, but in the mini projects, quite a few of them are dropped. So the goal is over the next many weeks, you pick maybe 2, maybe 3 mini projects, and that should meet the requirement if you do really well on all of those. Concept check 3A is due this Sunday, so that'll be over the basic multi-objective concepts that we've been talking about, Pareto-efficient sets, Pareto frontiers, and so on. And then 3B, due at the end of spring break, will be on specific multi-objective algorithms and Pareto ranking, something that we'll talk about today. So those announcements moving forward. Any questions? We'll talk more about the final project stuff and expectations on timing of forming your groups and all that as we get a little closer to the start of spring break. So last time we introduced the set-based idea of a solution approaches for multi-objective problems. The idea being that we can find a way to do as much computationally as possible before bringing in those subjective trade-off characterizations. So that's the idea, is that if someone just tells us what the multiple objectives they care about, but they don't tell us the weightings, that is a lot of information, and we can then exclude lots of solutions that are so-called dominated by other solutions. So solutions that can do that there are other solutions that can do better in all objectives. And so eventually we come out with a set of solutions, a Pareto-efficient set that cannot be dominated, and so we cannot just discard them. And then at that point we can say, all right, this set characterizes the trade-off among these criteria. There is absolutely no way for you to improve in one objective from a point on this set without degrading your response in another objective. And so at that point, that's where someone can look at the shape of that set or the shape of that frontier in the objective space, and then make some decisions about, well, I actually didn't imagine that there would be this weak of a trade-off. And so given how weak of a trade-off there is, then maybe I'm willing to give up on one objective because I don't have to give up that much of it, and in order to get a lot in another objective. So by holding the subjectivity towards the end, then it allows for a more informed way to set the weightings up and to better understand the costs and benefits, the opportunity costs, or as the economists would say, the marginal rate of substitution between the different objectives. And the nice thing about population-based solvers or evolutionary algorithms is that they naturally have set outcomes. So up until this point, we've been taking advantage of the populations and evolutionary algorithms as cute ways to sample the space and move the mean, to move sort of the center of the population around in an effort to find one good solution. Now we're looking for solvers that shape that whole population, and a little bit like the way CMA and ES did, it starts to shape the population, to shape it in a way that it's not just better informing sampling in the next few generations, but it's actually producing a set-based output that has meaning in its shape and what it's capturing. And so, we talked about this simple example last time. These two objectives, I plotted one on the vertical axis going up, the other one going down. And we said that the Pareto-efficient set is this area where there are no Pareto improvements. So we said a Pareto improvement is a point. If I can go to another point and that other point improves both objectives simultaneously, then that's a Pareto improvement. All of the red spots here, it is possible to make a Pareto improvement from them. The blue ones here in the middle, It's impossible to make a Pareto improvement from them. In order to make an improvement in this objective, you have to go down in this objective. And so we call these ones here the Pareto-efficient set. We might also call them the set of non-dominated solutions. And then, if we give this to our stakeholders, then we can invite, that's when subjectivity can really, that's the best place to put it. And a better way to capture this idea of a trade-off is not to plot things in this space where we actually make decision variables explicit, is to plot things in the so-called criteria space or objective space, where we're going to plot one objective against another, and you can have multiple. You can have, these could be very large, there's going to be a three-dimensional where the Pareto frontier will now be a plane instead of just it being a line here. But the idea here is that every dot here is one possible combination of the different objectives we care about. And if we're maximizing both objectives, then movement in this direction is movement that dominates anything in its wake. So that's the Pareto improvement direction. And so once you reach this point, it's impossible. So if you make, there are no points that are in the Pareto improvement direction. So there's no points in this kind of cone up here from any of these points. From these points, if I were to draw that cone, there are points inside it, and thus they're dominated. So this here, we don't have the ability to make any Pareto improvements, and that's our Pareto frontier. And here we see a pretty strong trade-off between the two objectives, because this is like a 45-degree line. And so that suggests that if you make, in order to make improvements in F2, so in order to go up in F2, you have to make a pretty strong degradation in F1. And so now these are incommensurable quantities. This could be in terms of speed. This could be in terms of accuracy, very different units. So our stakeholders may have a different relationship. So they could say, well, we're willing to tolerate, we might have to turn this. What the economists do is they end up normalizing this in terms of percentages. And so they will draw these spaces where the x-axis and y-axis, you don't think about the absolute amount you lose in one objective. You think about the relative amount you lose in that objective. And then you talk about this slope in terms of those relative losses, and that ends up being easier for them to conceptualize. But the point is, we can now start having conversations about this, this frontier, this set, this manifold, this line, as opposed to conversations about everything that's possible. So we exclude all of these bad solutions, and then we only have these. These are ones where you can, there would be an objective way to complain about any of these solutions. But here, I mean, somebody could choose to give you a design that's here, or a design that's here, a design that's here. And they've got their own reasons for why they slide along this frontier, but they're all defensible. These are not defensible. And that's the idea. Find the defensible choices so that then you can have more interesting conversations about how to choose among them. That's the Pareto frontier. And that's roughly where we left off last time. This is the major new concept in multi-objective optimization that Wendy introduced. So any questions about that? Yeah, I'll go, you go ahead.
Yeah, so I have a question regarding the area of like the Pareto efficient area. Is it that we usually take the max of two functions and then the whatever in between it would be the efficient Pareto?
Well, so I drew this as if there were two maxes, but we can generalize this to say, well, it might have been good to minimize this and maximize this. And so that's why we introduced this Pareto improvement idea and this efficiency idea based on it. So if that were the case, for example, that that I want to minimize F2 and maximize F1, then I'd say, well, from this point here, if I move in this direction, I'm maximizing F1, but now I'm making things worse in F2. So that switching that around may end up switching it so that actually now this is the Pareto efficient set and this is the dominated set. Yeah.
Right, like can be non-convex, what would that look like?
I'm sorry, what look
On the
like?
very final line on.
Oh, can be non-convex? That is, I will show you that. That's going to be as a little hint that's coming up. You know, like this is an example of a set of combinations where the Pareto front will be non-convex. So here we've got one objective that happens to have some oscillations, but it kind of is oscillations going up a hill. And this is another one that has oscillations that are kind of going up the hill. And when you combine them, all the blue points are all of the possible combinations of these two objectives. And if you were to try to think, what are the non-dominated solutions here? And we'll get to that. That's sort of, I don't want to give the punchline away, but the Pareto front would be non-convex. And so the Pareto front, so a convex Pareto front will be something that looks like this in the case of a two maximization problem. And a non-convex Pareto front will be something that, for example, looks like this. It's got shoulders here. So, and this idea of it dipping back, having this concavity, it turns out that there's a bunch of the early multi-objective solvers would skip this concavity, and that's a big problem. And we'll get to that. All right, so any other questions about this fundamental concept here of Pareto efficiency and Pareto optimality, Pareto frontiers? We're looking to find the frontier. All right, so now what can you do with this? If we had a solver for this, there's lots of cool things we can do. I mentioned that in general, we can do things with multi-objective, but it turns out the diversity that this maintains. So remember, it's going to try to, at equilibrium, instead of collapsing to a point, at equilibrium, so even CMAES ultimately collapses to a point. So these solvers will always maintain diversity if they're working well. And so their outputs are a diverse set. And so that suggests that there might be other ways we can use that diversity. And one of the examples which I brought up before is this so-called age fitness Pareto optimization. This is something that Lipson and Schmidt came up with at Columbia. It's popular in evolutionary robotics. So this is an idea where they're trying to solve a single objective problem. So they work with these like weird systems, for example, where they've got these little cubes of Jello that have pneumatics inside them that can inflate and deflate. And so they can stick together kind of like Legos. And so they can pulse like little muscles, and then they stick together. And then a question would be that if you can manufacture these things and they're just sort of constantly pulsing, how do you build them into shapes where those shapes can do useful things? So how do you design how to put these cubes together? And they build simulation systems, and then they can actually then generate these things. And they're simulation systems that are constantly trying different configurations of these cubes in this one particular soft robotics application. Then they use evolutionary algorithms to try to come up with these shapes to put these things together. And in this and other examples, they found that AFPO, age fitness Pareto optimization, works really well in a single objective problem. Like the objective might be try to get the thing to move as fast as possible. So they're not trying to do it as fast as possible and with as few cubes as possible. They're just trying to say as fast as possible, move in one direction coherently and as fast as possible. And so that is their single objective. But what they find is that in order to come up with these designs, it often requires sort of temporarily deviation or dips in fitness. Like you might kind of slowly be moving in one direction as these little things, these little soft robotic oscillators pulse. They might sort of slowly be moving in one direction. In order to make a change to that pattern, that ultimately moves in a straighter direction or a faster direction, it might require a temporary dip in fitness. So it might require adding a block that actually breaks the progress that was being made by the previous design. And by breaking it, that would normally be selected out. But if you just allow for another few mutations, then it actually leads you to a better body plan or a better shape of these robots so that they can actually start moving faster. And so what they want to do is they'd say, if it's a new innovation, if it's something totally new, we want to give it less of a fitness challenge. And so we want to keep it around even if it's doing more poorly than other things that are there. So what they said is, let's add an artificial second criteria, age. So we're going to maximize our fitness, maximize the speed of this blobby thing, but we are going to minimize the age of these designs, the number of generations that they're around. And so parents and their offspring continually age. So if you do a crossover between two designs, the offspring that come a crossover inherit the age of their parents, similar for mutations, but they are going to introduce new individuals randomly every generation with age equal to 1. So this means that you've got these existing powerhouses that are doing well, they have high fitness, and so they stick around. But then these new, totally random innovations that may not be very fit, they don't stick around, or they would normally not stick around. But because we're going to say that we not only care about fitness, we also care about age, minimizing age, then even though they are low fitness at birth, they stick around because they have the other criteria, their minimum age. And the older the population gets, the more ability to keep new individuals around, because now the high fitness individuals, they just get so old that they become, they get a big penalty in this age criteria, which allows for even younger individuals to stay in the population longer despite not having high fitness. So it's like initially, if everybody's young, you just need something that can at least move slowly in one direction. But once you've got something that is moving consistently in one direction and has been going around for a while, then you start experimenting with others and taking more risks. That's what AFPO does. So if you have a solver that can do this, then you have a way to actually add more evolvability to than a normal single objective solver. And so that's one example of, if we have a solver, some applications that we can do with that. I always forget to turn on the tape only. So that's just sort of summarizing. This preserves diversity by allowing young individuals to persist. So it allows us to, and this is an idea that we'll see come up a couple of times, it allows us to cross adaptive valleys. And so if you have your fitness function, so this is like the speed of the robot, you might be at a local maximum. So this is the fastest robot that you found so far, but there is a faster robot, but in order to get there, you need to make a lot of incremental changes, and those incremental changes will make you a slower robot until you make enough changes to be a faster robot again. Selection will typically only take you up these hills if you're thinking in a single objective sense. But maintaining diversity allows for you to so-called cross these valleys, so move in a way that seems to be going counter to fitness. And in this case, it is going counter to the single objective fitness, because the true fitness is somehow a blend of age and the old fitness. And that allows for these decreases in our main objective fitness, and then eventually gets individuals onto this peak, and then selection from this one can then take them up that peak. So that's the idea behind AFPO. So helpful in robotics when multiple manipulations are necessary before seeding improvements, allows you to get kind of a core level of background competency in a task, and then once you have it, then allow the rest of the population to start experimenting, doing lots of other things. Yeah.
Isn't there kind of a trade-off between innovation through this randomly generated new individuals and the offspring? Because it seems like there will be like the innovation for the older generations will be kind of capped.
You receive, yes, so you're saying that like if you're dumping population into the young ones.
Yeah, because for the older ones, there will be less potential to kind of come up with something new given what we've already had.
Yes, and that's that's sort of the risks that you're kind of taking here. The gambit is that once you get something that, if you think you live in this sort of a fitness world down here, then the thought is that if you're up on one of these peaks, there's probably no mutations that will take you off of this peak, and you're just going to fine tune around it. You'll just kind of get stuck here forever. So this is a thought, and this is what I mean by crossing adaptive valleys. It's a way to introduce new deviation and allow it to persist, even though it's at all these low fitness points. But you wouldn't want to, if you had to, see, this is the part of the reason why we don't want to weight objectives into a scalar, because you wouldn't want, like if you added these two things together into one new fitness function, you might say, I'm going to give 20% weight to this and 80% to that. You say, well, that's probably too much, because I don't just want to randomly be searching. Like, I really do want to capitalize on my successes. So then I say, well, maybe I'll do 80% here and 20% here. And we go, well, is that the right balance? And so what we want is a truly set-based fitness concept that somehow maintains diversity across these, so that if you happen to get too many solutions that seem to be, hanging out in this objective, then it starts bringing them down here. So it's almost, you need a frequency dependence, where if you're not making any success up here, then the algorithm will rebalance and start focusing more on this. But if you're making lots of success here, the algorithm will rebalance and then start innovating down here. And so that's what we're aiming for. All right, so that's AFPO, just an example. I think this will become more clear as we start seeing the actual algorithms used behind the scenes to make these multi-objective ones work. But just as an aspirational goal. Okay, so basically, before we jump into the first algorithm we see to this, just kind of wrapping up, the conceptual idea here is that we are looking for Pareto frontiers. So multi-objective optimization gives us a set, and the set of those solutions, the image, so when we say the image of the Pareto-efficient set in the objective space is the Pareto frontier. So ultimately, we're interested in the shape of that image. So, we can then start making conclusions about that shape. So here, you can see, what does it mean for a Pareto front to be almost vertical or almost horizontal? Well, that's one of those weak trade-offs that I was talking about. If you can show this to your stakeholder, or if you're the robotic designer and you look at these things and you say that's speed and that's accuracy or whatever, and this makes you realize that, well, I might really want F1 to be maximized, but if I take a very small hit in F1, I'll get a huge payoff in F2. So even though F1 matters to me and F2 matters to me, F2 matters enough to me that I'm willing to take a very small hit in F1 in order to get this F2. So knowing that this is almost vertical better informs me that maybe I shouldn't focus too much on a design that's out here, because the design that's up here doesn't really give me a lot of penalty in F1, but is a huge benefit in F2. And so seeing all of these designs together helps you make better sense of that. Similarly, if I do this and the algorithm comes back and it says the Pareto frontier is a single point, that can still happen. It's a set-based solver, but that set might be a single point. Everyone might collapse onto one point. What is the meaning of that being a single point? That means that it is possible for us to have our cake and eat it too, or eat our cake and have it too. It's possible to be maximized in both objectives simultaneously. In other words, there is no trade-off. So if things collapse to a point, you degenerate to two independent single objective solvers, where you're basically allowing yourself to optimize this objective, and you have absolutely no coupling to the other objective. So you can almost imagine optimizing this objective first and this objective second, or going back and forth. But there does exist a design which optimizes them both simultaneously. So no trade-off whatsoever. That's what a degenerate Pareto frontier looks like. Now, with that in mind, then I could ask the question, maybe a good exam question: is it possible in a two-dimensional Pareto context here to have a perfectly vertical, not almost vertical, but perfectly vertical or perfectly horizontal Pareto frontier? What do you think? Or why is the answer no? Why would we expect to never have a perfectly vertical Pareto frontier? See anybody else I haven't heard from?
because it will have multiple values for a single value of given objective.
And so what would that mean? So this is perfectly, if this was perfectly vertical, because it doesn't have to be a function. So it is, theoretically, it's possible to line up designs in a perfectly vertical line. But why would that not be a Pareto frontier?
Because I believe there will be.
What was that?
Because then it stops being an objective, like, and we've already achieved this, basically, one of the functions.
So you've achieved F1, there's no trade-off. So a perfectly vertical Pareto frontier is not a Pareto frontier. It implies the Pareto frontier is a single point. So that's how we get here. As the Pareto frontier goes from oblique to more and more vertical or more and more horizontal, at the point at which it becomes perfectly vertical, then this point up here dominates everything beneath it. And because of that, this becomes the Pareto frontier. Yep.
If they're not care about objective F2 at all, then it could be like perfectly vertical, right?
If you didn't care about F2,
Then there would be no trade-off.
well, then you would just do a single objective optimization. So the idea here is if you put F2 and F1 in there, you're saying that you at least care a little bit about F2. All right, so any questions about those visualizations there? So that's the type of thinking we want to try to embrace for this. The claim is that our evolutionary based algorithms are the perfect things to try for this. To this day, regardless of what single objective solvers you found out there, to this day, multi-objective solvers are really dominated by evolutionary algorithms because they do so well at populations where there's a potential for independent diversity, so decoupling among them together. So evolutionary algorithms and their population structure seem to be very well suited for multi-objective solutions like this. So how did the first multi-objective evolutionary algorithms do this? What were the problems? And how do the modern ones do it? So I have a feeling that as we go through this, this development, at least for me when I was in this point in my career, then these early multi-objective algorithms did it the way that my mind naturally went to. Like that was definitely the way I would do it. And so you can kind of see that that's where the industry went with, is to try it these ways. Then people discovered problems, and then they had to completely rethink fitness in order to come up with a solution that actually did better, that solved the problems of these past ones. And then people then rethought the original methods, and using some new math and some new appreciation for tournament selection, found a way to fix all of the old ones with a different way to scalarize. And that's where we got, for 3 objectives and higher, one that I'm not going to go into great detail in because I'm leaving it as an option for final project, is MOEA. So we'll probably be focusing on 2 objectives, and where that's NSGA 2 is like the dominant algorithm for that. But anyways, let's get into it. So historically, there were 2 big approaches. They're basically 2 versions of the same thing. Weighted sum approaches is the first case here. So the sort of some of the very first genetic algorithms to try to solve multi-objective problems were like this weight-based GA-MO, WBGA-MO, weight-based. And this, they just said, we're going to take a traditional GA that we already have implemented, and then we're going to take linear scalarization weights and add them to the chromosome, a little bit like the way evolution strategies adds mutation rates to the chromosome. And so you can just imagine every individual has decision variables, but then you augment that vector with the weights how that individual combines the objectives. So for me, this individual standing right here, it has a particular design, but it also does 80% objective 1 and 20% objective 2 and adds those things together. And that's how you calculate fitness for that individual. And then another individual, there could be another individual in the exact same point decision space that has different weights for its fitness function. And so across all of the individuals, you calculate fitness differently. And otherwise, you have to know to calculate fitness using that individual's weights, which when you pass in your fitness function, that can just be a part of the way you calculate your fitness function. I mean, your fitness function for individual X just has to be, X's weights times X's decision variables. And then that's, and so then you can just use a traditional evolutionary algorithm for it. It will do crossover and mutation on the weights, on the decision variables. Everything is identical to a traditional GA, but you just have larger chromosomes. And the thought here is that you're then going to optimize multiple trade-offs simultaneously, because some individuals are going to be rewarded for one mixture of fitness and other individuals rewarded for other mixtures of fitness. And then because you've got crossover and mutation, you just get a diverse mixture of combinations of fitness throughout the population. So that was one approach of that. Any questions about that? So that's just, there's not really a lot of innovation there. We're just going to make the chromosomes larger and put the weights in the chromosomes and then just let a normal GA do. So that didn't, so all of these have some success, but that didn't do a great job at covering the Pareto frontiers very well. It had no explicit pressure on diversity or uniformity across that Pareto frontier. So people started to come up with ways to slightly change the GA to make it move towards a more multi-objective structure. So random weight GA was a way to do that. So imagine you have capital K objectives. And so the idea here is you're going to draw a random population like you do with a normal GA. But a critical thing here is that when you calculate fitness for this generation, and only this generation, because you're going to iterate and then do it differently, but you're going to draw a random weight vector. So we draw for each one of our K objectives, we draw a random number between 0 and 1. We normalize them to the sum of those so that we get a bunch of weights, which all add up to 1. And then we just say for that generation, that random trade-off, that is the weight that we're going to promote. So for that generation, it might be 80% objective 1, 20% objective 2. For the next generation, it might be 40% objective 1, 60% objective 2. So every generation, the whole population is going to feel pressure. So it's like you've got all of these individuals, and for one generation, they get sucked towards one spot on the Pareto frontier. And then in the next generation, as they're moving towards that one spot, then suddenly the attractor moves, and then they get pulled towards another spot. And you keep doing that over and over again. And then the hope is that if you start out with enough diversity, you eventually kind of jiggle them toward the frontier, that they end up getting spread out along the frontier. So let me just finish the algorithm here to show that. So we're going to do proportional selection, fitness proportional selection. We do mutation and crossover, standard deal here. But we're going to use elitism, but we do elitism based on non-dominated solutions in the current generation. So that's another key update. So this is another innovation. This is an important innovation. We're going to see in a lot of algorithms that elitism is based on non-dominated sets. And so that's something we don't have in just the standard, this weight-based genetic algorithm. So as you're doing this, for the current generation, there will be individuals that relative to all of the other individuals, they're non-dominated. No other individual in the current population dominates them. That doesn't mean that they dominate, but that means that they're not dominated. So in theory, if we've got a good algorithm, if we keep track of all the non-dominated solutions, and if a previously non-dominated solution is now dominated by a new point, it gets kicked out. So the invariant here is this set E that we collect will always include points that are non-dominated. And so in theory, if we've got a good algorithm that's moving toward the Pareto frontier, E asymptotically will converge to the Pareto-efficient, to a sample of the Pareto-efficient set. And so that update to elitism is kind of an important thing here. So this is how we're adjusting our search directions to move sometimes towards one part of the frontier, sometimes towards another part of the frontier. And then as we're moving around back and forth, then we're updating our elites based on non-dominance. Area, not just based on high fitness, because fitness is constantly changing, but non-dominance, that doesn't change. And then we remove, so this is just updating that set, remove any now dominated solutions from E. And then this is another thing that they added in, randomly take this hyperparameter solutions from the population and then copy in individuals from the elite set. So this is kind of how these things together are sort of how, I guess, these three lines. This is a multi-objective version of elitism. With single objective, we just had a couple slots in the population, and we just made sure that those slots always had our top fitness individuals. But now we don't have a notion of top fitness. Oh, we do have a notion of non-dominance. And so we're going to keep track of our non-dominated solutions in E. And then that's just going to sit in parallel, a sort of separate memory of all of our non-dominated solutions that we constantly update so that nobody in that set is ever dominated. And then we have NE slots in our population that we will then pull in those elites so that those elites still have an impact on, they still help drive the evolution of new solutions. So the bigger this number is, the less exploration, the smaller this number, then the less retention you have. Same thing with a single objective. And then we check our stopping condition and iterate. Stopping conditions here are often just number of generations, but you can also check for convergence of, for example, the elite set, the non-dominated set. So if you haven't changed your non-dominated set in 20 generations, then maybe it's not worth continuing the algorithm. So either just run this for 200 generations or maybe run it until the elite set, which is really the output, if that thing hasn't changed for 20 generations. All right, questions about that? It's a minor change to its typical GA, random fitness functions every generation for everybody in that generation. So one fitness function for everybody in the generation, but every generation a new fitness function. And you keep track of your non-dominated set. Okay. Still based on linear scalarization. Key point. All right. So if you look back in the literature, there are a bunch more that are variations on this theme that are just randomly changing weights in different times, whatever, but it's still, they're all these weighted sum approaches where at some point you are calculating the fitness, which is based on some weighted sum, and you're somehow going to add some diversity in how you calculate the fitness. The alternative that you see, which is really just a subset of that, but people tried it because it seemed different enough at the time, is these alternating objective functions. So rather than calculating a composite fitness and then changing how you're calculating that every generation, what if you instead create either every generation, you just pick another single objective? And so it's, imagine if we did what I just said with the randomly weighted one, but instead of that, you choose a weights which are either 1 or 0. And which fitness function gets the 1 is what's being randomized each time. Well, that's a little bit like what we have here. You could do that for the whole population, or what this one does, vector evaluated GA, VEGA, it creates subpopulations every generation. And so it's imagine that we're starting to get into an idea which almost feels like niching, where we say if we have K objectives, we're going to create K subpopulations. And every subpopulation is going to focus on one of those objectives. But then periodically, we're going to allow for migration between the subpopulations to maintain diversity across the whole population, allow for innovation. When we talked about the 4 forces of evolution, natural selection, drift, mutation, I mentioned migration we don't really worry about for single objective. This is the first time we've actually started to see something that looks like migration start to drift, so to speak, into these algorithms. Right, so how does this work? Random initial population, we have to check our stopping criteria. We randomly sort the population into these K equal size subgroups. So each subgroup of a size is our main population, this is our number of objectives, this is the size of each one of our subpopulations. So we're going to randomly sort those. Sometimes it's called shuffling. And then for each objective, we assign a fitness to a subpopulation based on one of those objectives. So we just say, all right, we randomly sort them into K groups, and then we randomly sort the fitness objectives on top of those K groups. And then for each group, we calculate their fitness based on that objective assigned to that group. So there's no weighting of that. So for that group, then we then use a selection approach, so a selection operator. So this could be fitness proportion selection, tournament selection, whatever you like. Choose your selection operator, but you then choose NS solutions from that subpopulation based on that subpopulation's single objective fitness. And that creates a little set, PK, of the parents that are being contributed from just that subpopulation. So you do that for all of the subpopulations, and then you bring them all back together so that the full population is the union of all of the parents from all of the subpopulations. So now you've got parents that are optimized for speed, parents that are optimized for accuracy. I don't want to say optimized. Parents who are shaped by the pressure of speed, shaped by the pressure of accuracy, shaped by the pressure of cost, whatever. So each one of these parents are shaped by different specialization pressures. And you put them into a big pool together, and you allow them to commingle. So you allow them to mate. So now parents that have faced different specialization pressures are going to cross over to create offspring, which may be mixtures of those pressures, and mutate to sort of explore the space. So then we iterate back to number 2. So after we've generated offspring based on these specialist parents that come together and mix in these diverse ways, then we go back and we reshuffle them into subpopulations and start it all over again. And that there, that pulls these subpopulations along these single objective paths and shuffles them. And the hope was that crossover mutation across the whole group would create blends of different objectives. In reality, it really just creates these discrete groups of, because it's just hard via crossover mutation for this very little contact to create offspring that aren't broken. Or, I mean, the offspring are pretty much either going to be really good at mom's specialty, really good at dad's specialty, and they're probably off the frontier in the mixture of the two of them. So they end up, when they go back into the sorting here, then they end up just getting pulled back towards the specialty. So it's hard to maintain diversity along the frontier. You just get clumps at the corners of the frontier, up by F1 and up by F2. So really, these vector evaluated are just like random weighted ones, but you're forcing the weights to be ones or zeros. So it didn't really add a lot. So it's not very balanced. You get these clumps. Questions about that? Those are the two historically strong traditional ways to do multi-objective optimization. They had flaws, but they started people kind of along the right path in this thinking. But because they're all, even this one, effectively linearizations of single objectives into a scalarized objective, then they all suffer from the same problem with non-convexity, which is the next thing we're going to talk about. So, questions about that? Any of these before we move on? Okay, so, like I said, class 1, class 2, weighted sum, alternative objective functions have a lot of similarities. Key problem here is that you can add diversity mechanisms, which will be important, but they still fundamentally aren't great multi-objective solvers, and their dependence on linear scalarization is going to be a major problem with real multi-objective problems where each of your single objectives are complex enough that when you combine them together, you get Pareto frontiers, which are very interesting shapes. So let's look to see what I mean by that. So this is our general case. So imagine we have, we want to solve this maximization problem. This is the way we use for multi-objective. We'll often say we're going to maximize a set-based function. So I'm maximizing now a tuple in this particular case of two objectives. And that is implying that I don't have a weight for you. I just know that both of them are important. And I might have to do a negative in front of here, implying or maximize one and minimize the other. But this is our general problem. We're maximizing or sometimes minimizing a set of these things together. So these historical ways, their approach is effectively sweeping through different linear combinations of these objectives in the hopes of finding the frontier. So that translates this problem into this problem, where we're maximizing a weighted sum of two objectives. Now, if you look at that weighted sum, that is just a so-called inner product of a weight vector and of an objective function vector. It's a dot product of a vector of weights, which sets your trade-off, and a vector of your objectives, the actual evaluation of your multiple objectives together. So I can depict that. So I've got my criteria space here, objective 1 on this axis, objective 2 on this axis. If I plot all of those objectives together, then I get potentially a non-convex Pareto frontier. So I get something that instead of looking like a nice curve like this, it's got this bump in it. And so we'll see if this is going to be an issue for these linear combinations. So how do we depict graphically what this is doing up here? Well, if we think about these weights, like imagine we're sweeping through weights. And so at any instant, we have one weight chosen, like in the randomly weighted genetic algorithm. At the top of one generation, you pick the weights and they're set for that whole generation. So really what you're doing is you're setting this, you're creating a new axis, which represents the particular balance of trade-offs that you care about. So this line right here, it has a rise of W2 and a run of W1. So its slope represents the balance between the weight, these two weights that you've chosen for this particular objective here. And so maximizing this function is the same as saying, I would like to look at all points on this combination of objectives so that if I pick one of them, if I project it, so I shine a light, so I've got a little light source, I shine a light and I see a shadow of that light on this dashed line here, which represents the particular trade-off between 1 and 2 that I care about. Then the shadow that is cast on that axis right there, I want to maximize that. That's what this is doing. That's what maximizing a dot product is doing, is I'm saying I've got this vector and I've got this vector, and I want to sort of, ideally, so I want to make it so that I'm sort of calculating, you can view it as calculating an angle between these two, but that's not quite right here because the length of this thing matters as well. So it really is saying that every one of these vectors can be decomposed into a component in the direction of the desired trade-off and a component orthogonal to it. And really what I'm saying is for every point, I want to find the point whose component in the direction of my desired trade-off is maximized. Does that make sense so far before I jump into why convexity matters here? Yeah.
Yeah, so this one is F square.
Oh, so, okay, I'm sorry, that's a notational thing here. So I've hidden this F1, so I'm gonna say this is, because I'm trying not to give away the punchline, but I'm gonna say consider solutions. It's not meant to be a square, I just ran out of scripts. F1 and F2. And so there is an F1 up here that I haven't uncovered.
Okay, so F2 is a solution.
Yes, F2 is solution, not F squared. So this is the first component of F2 and the second component of F2. Yeah.
Like, wouldn't it miss off a solution?
That's what we're gonna get to. That's exactly the problem we're gonna get to. So, but before we get to that, as everyone understand this framework so far. So we only have the option of choosing along this line here, this non-convex frontier. And so we're trying to use this to find that Pareto frontier. And the question is, how much of this Pareto frontier can we find? All right, so this was our F1. We projected it this way. This is how far it is. There are better solutions. So there is, and maybe I should have made this one F1, not F2, given that I was going to present it in this order. But now imagine we have another solution up here. I mean, it's right there on the Pareto frontier. Let's consider that solution. That solution here, when I project it down, it has a much bigger component along the trade-off direction that we care about. So this one is a higher value than this one. So if I am trying to maximize this single objective, this combination, I will exclude this one and I will take this one instead. So as a consequence, if we ask the question, how much of the Pareto frontier is accessible with this approach, then it turns out only parts of it that intersect with the so-called convex hull of the Pareto frontier are accessible. So I can highlight that in that if, I could say, I'm highlighting in yellow, this portion is accessible, but at this point, anything under the dotted highlight is not accessible. So we're only going to be able to solve for red. We're only going to be able to solve for here and down here. These are totally reasonable trade-offs that we should be able to present to our shareholder. These ones right here, our stakeholder, but they're shaded by the heavy shoulders of this. And so we can only find things along this convex hull here. And so these end up being hidden from this approach. And every single multi-objective framework that is based on a linear scalarization is going to miss those. Yep.
Why is it that you can even see the ones that are convex, but not straight on the line? What exactly is the I don't know if that makes sense. If all of this is being projected, wouldn't the things that are projected over there still fall under that maximum F1 that you've shown?
You mean, are you referring to these or?
Yeah, the ones on the highlight, yes.
And you're asking, and so the question was, why can we see them, or what do you mean?
Why can we see them if you project it onto that maximum line, wouldn't they still fall underneath what you've currently labeled as W1?
Oh, I see what you're saying. So, I mean, the idea here is that for this, that's a great question. For this trade-off, this ends up being the maximum. This would be the point that is found. If I configure W1 and W2, just for that subproblem, it would find this point right here. But if I configure W1, W2 to be a different W1 and W2, then it would give me a different line. And for this line, this would be the one you'd find. So that's what's sweeping these things around. It's taking this dashed line, and the approach here is to take this dashed line and to sweep it all the way this way and sweep it all the way this way. And for this ray that comes out here, for every one of those W axes, those trade-off axes, we solve this projection problem. And if you do that across all of those, then you will only ever find these points and these points. You'll never find these points. Does that make sense? Yep.
This kind of goes away if we make an assumption about convexity. So
if you make an assumption about convexity.
Yeah, so it's used in economics a lot.
Great question. So, when economists say that utility has this sort of scalar combination, linear combination, then Yeah, you can, then there are some, I think, assumptions there about, I think a lot of those, the thing is, I think economists understand this problem, but very often they don't need quantitative solvers, but they need a conceptual framework to understand things like utility curves, ISO utility, consumer choice, all this sorts of stuff. And if they do need to push down and do a quantitative solution, they take all this into account and they would recognize that they'd be shading off some of these things. But if you just go into a microeconomics course, a 200-level microeconomics course, where you're drawing curves that look a lot like this, and you start drawing these like ISO utility curves and tangents and all of that. So if you've ever taken a consumer choice course or a micro course, probably seen a lot of that. It's just easier to teach at that level, assuming that you have convexity. But and then I think a lot of the goods, it's actually sort of coincidentally called this good, but in economics, we refer to goods as these things where typically more of them is better. And so there's always this sort of assumption that more electricity is better for me, more water is better for me, and so on. This idea, which is not something we have in engineering necessarily, this idea that there could be too much of F2. And like in economics, we care about the trade-off between them. So we care about diminishing marginal returns. So in economics, we say it's always better to have more of F2, but eventually you get to a point where the cost of getting more F2 is better spent to get more F1. And in those cases, then these individual objective functions all look like this. They don't look like this. Certainly not, this. But in engineering problems, like training neural networks, for example, or just trying to figure out the best combination of stiffness parameters for a soft robotics GUI or whatever, then you find that individual objectives have their own separate, you actually do have these individual peaks. And that's really the problem. When you start having complex individual objectives and you combine them together, then you get these concave Pareto frontiers. Does that make sense? Okay, so that's the problem. So to demonstrate that, so here's, I showed this before, I plotted this in MATLAB. So you can see, so I just came up with these numbers. I said, I want something that's kind of sinusoidal, but it also kind of sits on a hill, and I'm just going to pick two of these. I picked these kind of randomly, and I got this guy. This is actually sort of when if you go to a course where you talk about this stuff, this is sort of a canonical example. It's kind of stair-step looking problem. And so when you look at this, you'd say, like, these are all the combinations of objectives. So some of these are not in the Pareto front. So your optimizer is going to be constrained to sampling from this space anyway. So then you have to ask the question, what is in the Pareto front? And then I hope we see that for sure, this is in the Pareto front. All of these points, none of them are dominated. To be dominated would mean that there have to be points up here, but these are not accessible. There are no combinations of decision variables that achieve objectives in this space. And so all of these are safe. They're in our Pareto frontier. But a linear solver would take the convex hull of this thing, and it would say that only those points there, that top line and these peaks are in our Pareto frontier. But in reality, our Pareto frontier, like these points here, these are also non-dominated. So our stakeholder needs to know about those combinations. These points right here, these are also non-dominated. Our stakeholder needs to know about those. So we need a solver that can solve for those. And in MATLAB, they have something called GA multi-obj that finds those. It uses this algorithm NSGA2 behind the scenes, and it's able to find those. If it used WBGA, RWGA, VEGA, any of those, it would not find these here. Does everybody see why that's the Pareto front for this problem? Okay. And then, so here's another example. Again, what I just came up with. Just put this one in. I thought it looked kind of cool. So here is an objective function, seems like a totally reasonable objective function, doesn't look very different than the objective function I gave you for mini project 1. Similarly, this does not look that different than the objective I gave you for mini project 2. If you buy that for mini project 1, those were reasonable single objectives, then it should be reasonable that when you combine the two things together, this is a reasonable shape of the accessible space in the criteria space. So what do we think is the Pareto front? So how many people think that this point is in the Pareto frontier? No. So a tip that I do is if I can draw a cone, I kind of call it the Dominion cone. If any points land in it, it is dominated. So this one is dominated by this one. And to be tricky, here, I'm assuming that I'm maximizing both of these. So if I wanted to minimize one of these, I need to redraw the Dominion cone. I need to sort of say, well, anything above this, but below this. And so now this would be the points that I look for domination. But in this case, because I'm maximizing both, then that's the shape of each one of my Dominion cones. So any point along this frontier where I can draw one of these little Dominion cones and nothing is in it is in the Pareto frontier. So I hope you can see that if I draw kind of a horizontal line this way, and if I draw a horizontal line this way, then it sort of identifies that my Pareto frontier is going to be everything here, and then a little bit out here. And I'll highlight those without the at there. So let me just highlight those and then see if there's questions about that. So I'm going to say the Pareto front is, I'll just draw a dashed line for my reference. Maybe I'll make it gray. So I'm going to draw this thing roughly horizontal. Maybe I'll make it dashed. So roughly horizontal line out to here. Roughly horizontal line from this peak to there. Pull it up a little bit. One more time. All right, that's good. And then I'm going to highlight the Pareto frontier, where it'll be everything here, because none of that is dominated, none of this is dominated, and none of this is dominated. Everything else is not on the Pareto frontier. So if I were to run GA multi-ob on this, that's where it would highlight. So everybody see that, those three green regions, why those are non-dominated. And if I were to run an old school 1980s multi-objective algorithm, I have to think, what's the convex hull? And it'd be like roughly this thing. So it'd be everything that touches that convex hull and nothing underneath it. So it'd be like these points up here, this point here, maybe this point down here. That makes sense? Okay. So a good question is, what else can we do if we can't do the linear combinations? Well, this is where inspiration from biology helps again, because biology is a multi-objective beast. We don't think about like fitness is the only objective that matters, but there are multiple ways to get at fitness. There's multiple, a phenotype is a complex thing. It has lots of characters. For one organism, it's good to be fast. Another organism, it's good to be slow, and so on. So, I'm looking back at my objective space, F1 and F2. But if we wanted to, we can think of this as X is a chromosome and F is a character 1 and character 2. And so each one of these points we could think of as a different species, a different organism that combines characters, traits. So each one of these have different traits, but these traits are easily dominated by others in the population. So this one is dominated by that one, and so on. So that domination, that means that you're the squirrel out there that is not only slow, but you're also like very bad at finding your nuts, despite like, caching your nuts, like you have to search for them. You think if you're slow, you'd at least loiter in an area, maybe you at least got that going for you. But if you're both slow and really bad at finding the cached nuts that they save there, another squirrel is likely to be both faster than you and better at finding these things. And that other squirrel is going to be more likely to have offspring. So this sort of suggests that any trait combinations that are back here are going to be purged from the population in favor of trait combinations that are up here, that are higher up here. So this is suggesting that we need a fitness concept, which is basically, proximity to what is going to be this Pareto frontier. So, that Pareto frontier there, it doesn't really matter where I am on the Pareto frontier. I'm higher fitness if I'm closer to it. So I need that sort of fitness concept. And then once I'm on that Pareto frontier, then I want something which encourages coexistence along the frontier in these little niches. And those niches are those individual trade-offs. So that coexistence is going to basically make it so that I want crowding out. So I don't want lots of solutions all here. If I have enough individuals in the population, I'd rather one individual stick with this niche and another individual go to a nearby niche. So I want competitive exclusion within the niches, and I want, so crowding, but then I want coexistence across the frontier into multiple niches. So that's what I need. I need a fitness concept that brings me toward the frontier, and I need a diversity concept which generates niches. And so the fitness concept we're going to start with is called Pareto ranking. And so the idea behind this Pareto ranking is it's going to end up counting how dominant you are and using that as your fitness. The trouble with this, and we're going to go into what Pareto ranking is here, the trouble with this is there's going to be many different paths to higher fitness. That theoretically can allow for diversity, but it's also going to create complications because it also welcomes in things like drift to come back, because it creates a whole new way for neutrality to act. So if all of these individuals are equal fitness, then how do we maintain diversity? That's like a giant fitness plateau. So now we're not just saying that make your way to the plateau, but explore the plateau and maintain diversity across the plateau. So that's kind of a key challenge here. Fitness degeneracy, it has a pro and a con. The pro is that it allows for multiple paths to get to the plateau. The con is that it makes it difficult to maintain diversity across the plateau. All right, so that's the general perspective. So we're going to see the term niche come up over and over again. So a lot of kind of hints, and things will sort of be giving community ecology throughout all of this. So Pareto ranking. So why don't we start to introduce this? And this will bring us almost to the end, and so we'll be able to wrap up next time. But so Pareto ranking, there's a bunch of different ways we can do ranking. All of them are based on the idea that we can judge whether a solution candidate dominates another, or on the flip side, is dominated by another. And we can count up things like how many solutions dominate you and how many solutions do you dominate. Those counts of dominance can be then used to generate a fitness concept. And that's all I'm sort of saying up here. So, so imagine this picture down here, objective 1, objective 2. I've got 1, 2, 3, 4 candidates, and I've got a fifth right here that I'll take out there. And this is where I'm introducing that dominion cone that I just hinted at before. So if I'm saying that I take whatever if better is going in this direction, I take those two directions and I position them on top of my candidate. And then anything that's in the resulting cone between that, those dominate that solution. So if I look up here, this solution, this blue solution, is not dominated by any of the other solutions. But these solutions, green, red, and orange, they are all dominated by a single blue one. And then this black solution, it's dominated by all of these four. So we're seeing by these counts of who's dominating who or who's being dominated by who, it suggests that we can now sort individuals by their dominance tier. So it kind of hints at that we can build fitness based off of dominance. And there's three different ways that major algorithms do this. So the first way here is you rank by how many others that the focal solution dominates. So here you want higher is better. So here, this blue one is in the dominion cone of all of these three plus this one here. So it is rank 4. So having a rank 4 is better than having a rank 1. All of these three all have rank 1. So this band is a band of rank 1 because they all individually have the blue one in their dominion cone. And then this black one down here is rank 0 because okay, I said that backwards. These are all rank 1 because each one of them are in black's dominion cone and not anyone else's. So this one is in 4 other individuals' dominion cone. These are only in 1 other individual's dominion cone. This one is in no individual's dominion cone. So it dominates 0, these dominate 1, this one dominates 4. That's how we count those up. And that creates these isofitness sets, these equivalence classes, where there only happen to be 1 that is of fitness 4, there are 3 of fitness 1, and 1 of fitness 0. Now, if you're going to use fitness proportionate selection, you can't have a 0 fitness. So very often they add 1 to these. So this would be rank 1, this would be rank 2, and this would be rank 5. Okay, so I just wrote that out over here. So any questions about this idea? I'm ranking by how many candidates you dominate. The problem with this, which is used in this, I forget what SP, it's like strongest Pareto evolutionary algorithm, something like that. So these multi-objective algorithms that use this, a problem with this is it adds a lot of selective pressure. It purges diversity very quickly if you don't then scale that fitness afterwards. So you can see that if you happen to be very close to the Pareto frontier, you might have an extremely large fitness relative to those which you would think should be kind of close behind you. So this jump from 4 to 1 is, unless you scale that down with a fitness scaling function, might mean you're going to kill off these and only be left with this one. So you are getting closer to the Pareto frontier, but this green one, with a little bit of work, might have been able to get close to the Pareto frontier in another direction. And now you've killed off that green one because its fitness was so far behind that. So other methods, like this ranking approach 2, let's flip that. We're going to rank by how many others that dominate the focal solution. So lower is better. So in this particular case, and this is something that's used by MOGA, the multi-objective genetic algorithm. So in this case, we say that the top solution is ranked 0 because nothing dominates it. The next 3 are ranked 1 because only 1 dominates them. And then the last one's ranked 4 because 4 dominates it. And lower is better. So this seems to improve things because now, at least at the top of the fitness ranking, the higher fitness solutions, there's not as much difference. So you maintain diversity at the top, but then you very quickly purge diversity at the bottom. Maybe that's okay. Maybe that's a feature, but you could argue that that could also be a bug. And then I'll start with these two next time to remind us of this. But then the last one, which I'm just going to put out here just to let it kind of marinate, is what is used in NSGA 2, which is sort of the dominant multi-objective algorithm, where you do iterative rank peeling, where you say, here are all my solutions. First, I'm gonna take anyone in the non-dominated set out and I'm gonna give them rank 1. So this is the only one in the non-dominated set. Remove them. Now I'm going to then say who's now in the non-dominated set. Well, now these 3 are in the non-dominated set. I'm going to give them rank 2. Remove them. Now that I've removed all of those, who's left in the non-dominated set? This one's left in the dominated set. They get rank 3. So the nice thing about this is you've got what we refer to as a dense ranking. There are no gaps in the ranking. And so this has sort of the weakest selective pressure, so it has the highest ability to maintain diversity, which is really important as we approach the Pareto frontier. All right, I don't want to keep any longer. Any questions, feel free to come up. We're going to pick up here, and then we'll transition to multimodal for the next unit, and that will actually dovetail really nicely with the end of this unit, which we're almost there. Okay, thanks everybody. Have a good weekend. And if you have any other questions, feel free to come on.